All in all, Einstein's theories predicted that compared to the earthbound clock, the eastward-flying clock should end up being up to 60 billionths of a second late, whereas the westward-flying one should be about 275 billionths of a second ahead. The experiment proved him right. You may not find that so impressive because the time differences above sound tiny. And they are. But remember that a plane doesn't fly that fast, and Earth isn't that big a cosmic object. Fly faster or get close to a gravitationally much more powerful object in space, and the time difference can become huge, as you've experienced in the near-light-speed plane in your dream. Needless to say, the precision of Haffel and Keating's experiment has been improved upon ever since 1971, confirming its result with increasing levels of accuracy. Space-time indeed means what it means. It is a mix of space and time. Within our universe, clock-ticking rates depend on who is looking at them. It depends upon where you are and what is next to you and on your speed. At the beginning of the 20th century, this was very abstract. Today, it is an experimental fact. We all have to accept it. In this universe of ours, time and distances are not universal concepts. They depend on the observer, on who is experiencing them, and on who is looking at them. They are both relative. Otherwise, the speed of light would neither be fixed, nor a limiting one. Now, what has mankind made out of this knowledge? Did it change our everyday life? The bit of it that is purely related to velocity did. Yes, a lot. Not only does our technology often make use of fast-moving particles to convey information in all manner of transmissions, special relativity also helped us understand how all the matter we are made of works. As you shall soon see, electrons within the atoms that make up your body and pretty much anything else in the world of the very small move very quickly indeed. As far as gravity and space-time go, however, as amazing as it may sound, only one mass-market device has so far been built that makes use of their relationship, GPS. Anytime you check your position with a GPS device, whether on your smartphone or in your car, you use the fact that space and time are curved around Earth. The closer you are to the surface, the steeper the curve, not only in space, but in time too. There are clocks up there within the satellites that communicate with your GPS device to localize it. If no correction was made to take into account the time-ticking difference between the ground and the satellite, your position would quickly come out wrong. It would drift by about 10 kilometers per day. GPS would be useless. It is thanks to Einstein's special and general theories of relativity that GPS works. All right. That's how it is. There is no such thing as a clock that ticks the same way throughout the universe. Now, at 99.99999999% of the speed of light, the plane in your dream traveled incredibly quickly through space compared to Earth and all its inhabitants, and you landed in 2415, and you can consider yourself lucky. Had you flown even faster, you would have arrived even further away in the future. How much further? Again, it depends on your speed. But there is one limit, because nothing can travel faster than light. To travel as fast as light could maybe be possible one day, but you'd need to make a huge sacrifice. You'd have to get rid of your mass. All of it. Light cannot carry any mass whatsoever, and that is why it travels so fast. Light travels light. What's the matter with matter? You may rightly wonder. You experienced it yourself. Everything that is massive becomes more massive when accelerated too much. To reach the speed of light, one must therefore have no mass to begin with. Still, what would happen if you were able to transform yourself into a massless being of some sort? How, then, would your time flow? As shocking as it may sound, the answer is that it would not flow. The ticking of any clock you had with you would just stop. At the speed of light, time freezes. Completely. And that is the reason why the light that has traveled throughout the universe to reach us today is exactly the same as it was when it was emitted. Unlike a postcard that, after 13.8 billion years, would be tattered and ripped by the journey and resemble nothing close to what it once was, the images that are carried by light throughout the cosmos are not affected by the passage of time. When we gather light originating from the furthest reaches of our visible universe, we get pictures of the universe as it was back then. 25. Now, being made of mass, you have no choice but to be subjected to the passage of time. There is nothing you can do about that. To become eternal, you'd need to turn yourself into light, which can't be done. Still, if you could, then your time wouldn't flow anymore at all. You'd be eternal indeed, but unaware of it. That being said, despite the impossibility of being eternal, you may, even though you are massive, be able to reach a future unreachable to your neighbors. For this, you'd just have to travel fast, like your plane did. Or to settle on a gravitationally much more powerful planet than Earth. To wrap up the subject, I know that some of you, for one reason or another, do not like the idea of aging and would very much like to remain young for as long as possible, or at least much longer than your neighbor. Well, to you, special readers, I now address the following warning: there is no point trying to run quickly or to become a Formula 1 driver or even a test pilot for the RAF. There is even no point trying to board a plane to fly at 99.999,999% of the speed of light. Why? Because your clock won't ever change from your point of view. To your eyes, and in terms of the cells that make up your body, a second will forever and always be a second, a day, a year, and so on. Your personal time and aging won't slow down, you won't live longer, your cells will still grow and decay at the same rate, and that will be the same for everybody traveling with you. Traveling fast or living on a much denser faraway planet won't make you live longer, because to you 24 hours will still feel like 24 hours. However, other people may see you live longer than they do. Fast-forwarding your present to quickly reach another person's future is theoretically possible. 26. But living longer by traveling fast isn't. With Einstein's special and general relativities, you've discovered that a truly weird world surrounds the one we have access to through our senses, the one we live our daily lives in. But what you've seen so far is nowhere near as weird as what you are about to experience once safely back in your home. After the very large and very fast, it is now time for you to enter the world of the very small. And I am afraid that if you did not believe in magic before, you might have to start now. Part 4. A dive into the quantum world. 1. A lump of gold and a magnet. Your great-aunt has left. You did ask her to stay for a few days, if only to have someone to discuss your strange relativistic dream with, but rather unexpectedly, she declined the offer. All things considered, she found you well and sound, felt she had played her part in bringing you back home, and boarded the first flight to Sydney, leaving in your care the whole collection of crystal vases she had brought to cheer you up. She's back in Australia now, and you are back home. On your sofa. Looking at her awful vases while toying with a small magnet in the shape of a palm tree that you bought in a souvenir shop, to remind you of your tropical island. You still have a week before getting back to work, 7 days to find as many ways as you can of ridding yourself of all those vases, but you hesitate. Have you finished with your adventures in the hidden nature of reality, or is there another level of understanding still to come? Finding no straightforward answer, you stand up to make yourself a hot drink. Pottering about in the kitchen making coffee, you suddenly spot a brick that, curiously, sticks out ever so slightly from the wall. Surprised, you pull on it and it slides out. To your astonishment, behind it lies a cube of gold, probably hidden there by some former tenants. It is half the size of your palm and thus worth a small fortune. How you could have not spotted the brick before is a mystery, but there are arguably no better homecomings than those when you find some gold in your kitchen, so you don't think about it too much. You pour yourself some coffee and look at your treasure with a cunning smile. You have journeyed through the cosmos, the realm of the very big. You've traveled fast as it is possible to go. But you do not have a clue about the world of the very small, what matter is actually made of. Is gold made of small bricks? Why are the materials that surround you so different one from another? Why is gold different from cheese? Why aren't we liquid at room temperature like water is? With a grin, deciding to put science before money, you cut your gold into 2 equal parts to see what is inside. Unlike some cheeses, the inner parts of the gold bar have the same color, the same absence of smell, the same everything as its outer surfaces. You nonetheless cut one of the halves in 2 again, and again, and again, frantically looking for some change as you get smaller and smaller chunks of it. It seems to be gold all the way. One might think that this cutting could go on forever, but no, it does not. After 26 or 27 halvings, you are left with the tiniest possible piece of gold there is. Cut it once more and you still get something, but it is not gold anymore. This elementary amount of gold, the tiniest thing that is still gold, is what scientists call an atom of gold. Note that although it may seem that having something 26 times isn't much, it is. You would find it rather hard to do it at home. To give you an idea, were you to do it the other way round by, for instance, tearing off a page of this book before folding it to double its thickness 26 times, you'd get a stack about 14 kilometers high. Another way of expressing this is to say that you'd need a mountain 50% higher than Mount Everest to start with if, by having it 26 times, you wanted to end up with something as thin as a page of this book. Only the best modern technologies are able to look at a single atom of gold. 27. What about lead, or silver, or carbon? Any other pure material you'd have found instead of gold would have led you to the same conclusion. Have a piece of it that fits in your palm again and again and again, 26 times. Give or take 1 or 2, and you end up with an atom, something that cannot be broken anymore, without becoming something different from the material you started with. Cheese, on the other hand, is not a pure material. But it is made of atoms too, atoms that are stuck to each other. All the matter we know of in our universe is made of atoms. So what are the atoms themselves made of? You cannot tell yet, but you have a hunch that they are full of smaller constituents, and that these tiny pieces are the same in all the atoms throughout the universe. You will travel within their world very soon, but I can already say that it is because the number of these smaller constituents differs from one atom to the next that pure materials have very different properties and thus, as everyone knows, value. Any broker would certainly wonder about your sanity were you to try to swap a kilogram of mercury for one of gold or plutonium on the basis that they're all made out of similarly structured atoms. So what are they, these atoms? What gives materials made out of them such different properties and shapes? And why can you cut through butter with a knife, but not through a diamond, if everything is made out of the same stuff? With all these questions stacking up in your brain, you leave them to fetch some milk for your coffee. As you approach your fridge, you mindlessly grab your palm tree magnet to stick it to your refrigerator, but as it leaps out of your fingers to settle itself right against the metallic door, you freeze. Until now, such an action, for a magnet, was familiar enough. But it is not anymore. How do magnets do that? How does the fridge know that the magnet is coming? Or is it the magnet that knows the fridge is there? Or both? Or is it just pure magic? As far as you know, you've never ever seen anything being exchanged between a magnet and a fridge. No spooky hand reaching out from one to grab the other and pull it against its surface. But maybe you simply did not look carefully enough. You unstick the magnet from the fridge and stare at its surface, on the back of the crudely crafted palm tree. As far as you can tell, the dark surface is flat. Focused, now holding it very tightly between your thumb and index finger, you press your cheek against the fridge door, staring carefully at the air, and bring the magnet closer to it again. It is a few centimeters away. You feel something. A force. An attractive force is pulling the magnet towards the fridge. Or the fridge towards the magnet. Or both. Hard to tell. But in the air, nothing. That's for sure. You can't see the slightest hint of anything happening that could explain how they are aware of each other's presence. The magnet is now about half a centimeter away from the fridge and the pulling force is getting much, much stronger. You even have a hard time keeping the magnet where it is. And still nothing visible. You let go. The magnet jumps from your fingers to the door, where it sticks still, as happily settled as you are curiously puzzled. For centuries, many men and women have wondered about this strange attraction. It is spooky, isn't it? The magnet jumped. Nothing happened before it touched the fridge, and yet there was a force. That's what our ancestors thought when they looked at magnets, so even though they did not have fridges, they began to talk about a spooky action at a distance to describe the invisible something that makes magnets work. It is a bit like gravity, really. No one can see gravity. When Newton came up with his amazing formula to describe how objects, throughout the universe, are attracted towards each other, he had no clue what was responsible for the gravitational force he was describing. Einstein found out, though, about a century ago. Gravity is not a force, he told us, but a fall. A fall down spacetime curves. So is it the same with magnets? Do magnets create steep curves in spacetime too? No. That can't be it. Or everything would fall towards them, not just nails, iron filings, and other potential magnets. You've never felt your own fingers being pulled by a magnet. No, something else has to be found. And something else has been found. About 80 years ago. It involves what we call a field. A quantum field, to be precise. And now that you know about the existence of atoms and magnets, you are about to see what a marvel a quantum field is. Too like a fish in the sea. Imagine for a moment that you are a fish, and that for some reason you've decided to see what lies above the ocean that is your home. From the depths, gathering as much speed as you can, you shoot upwards, like a torpedo. You are aiming for what we humans call the surface, but what you, a fish, probably call the ceiling. You swim fast. Then faster. Water slides against your scales. The surrounding light gets brighter and brighter as you move closer to the end of your liquid world. Presently, you're out. There's no more water around you. You are flying through some blue emptiness. You flip your fins as hard as you can, but there's no way you can swim higher. Unlike a bird, indeed very much like a fish, your voyage upwards comes to an abrupt end. Sliding down the space-time slope created by Earth's presence, you splash back into the ocean. Some time later, back in the salty depths of your liquid home, you discuss your experience with some fish friends of yours who share a similar taste for the unknown. You promptly agree that up there, above the ceiling of your immense liquid world, it is impossible to swim. Above the ocean, you conclude, there is only blue emptiness. We humans know better. We know there is air above the ocean, and we now know that what we call air is far from being nothing. Deprived of it for more than a couple of minutes, we die. Most of us, however, are not much wiser than the fish under the sea. Don't we all kind of think that in outer space, above the atmosphere, beyond our precious air, there is nothing at all? Don't we believe that space is but black emptiness? As you are about to see throughout the rest of this book, that is a mistake. Outer space is far from empty. When, as a fish, you briefly jumped above the ocean's surface, you entered another world, a world mostly made of gas and dust, not liquid. Now, the world you are about to enter is much more widespread than that. It is called the quantum world. It is the world of fundamental matter and light. Unlike the sea, which is made of water and stops where air begins, the quantum world is everywhere. In the sea, in the ground, in the matter we are made of, in light, and in outer space. Even in empty space. To enter its realm, however, has taken mankind millennia. The doors to the quantum world are buried deep within the very small. And because the air and gravity and many other things can mess up the picture, we are about to forget about them for a moment. And the best way to do that is to send you back into outer space. As you pull your magnet away from the fridge door to check its surface again, you see no visible change there whatsoever. Still black. Still smooth. And yet you felt the force. No doubt about that. How weird. You press your cheek against your fridge once more, to do the experiment one more time, and you are so focused on it that everything but the magnet and the fridge vanishes around you. The floor, the air, your lump of gold, the walls, your whole kitchen and your flat. Gone. Your hometown. Gone. And so is Earth and the moon and everything else. You are floating in outer space, in a world of thoughts that obeys the laws of nature as they are known today. There is no air around you. There is no gravity either. There is nothing, really, apart from you, the magnet, the fridge, and whatever it is that makes magnets and fridges interact. By now, you should be used to this kind of situation, so you do not worry too much about it and focus on the task at hand. Your cheek is cold against the fridge's door. The magnet is still in your hand. You set it loose and, at the very moment you let it go, a new kind of adventure begins for you. You start shrinking. Throughout your journeys through space-time, you looked upon the universe from a rather large perspective to get to grips with the very big, and then you had to see the world from the point of view of extreme speed, so you traveled extremely quickly. Now you are on your way to discover the quantum world, so you shrink. A lot. You are becoming a mini-you. A mini-you who is a couple of atoms tall. How small is that? Let's see. As you are reading this, your book, or screen, is probably just a few hands' breadths away from your eyes. The smallest thing your sight can perceive from that distance is about 1/20th of a millimeter thick, 1/3 of the width of a human hair. Right now, your mini-you has shrunk to a size 100,000 times smaller than that. About the right scale to see if there actually is anything happening in between your magnet and your fridge. Focused, although somewhat taken aback by the shrinking, you look around for spooky hands reaching out from one direction or the other. You turn your mini head left and right and up and down. You do not see anything at all. You know the magnet is somewhere to your right, and the fridge somewhere behind your left ear, but from your new perspective, they are too far away for you to see them. So you wait. And nothing is happening. Nothing at all. After a rather long moment of pure solitude, you decide to try something else, rather than seeing, feeling might do the trick. Like when you were a kid and, to kill time, pretended you had superpowers. You virtually breathe in and out a few times, for concentration, and then you switch off your sight. You are like a minuscule yogi in space. Tinier than dust. Eyes closed, you slowly spread your arms as you've seen people do in movies. At first, you do not feel anything. And then, you do. You have the impression of being a fish in the sea, as if everything around you was bathed in some kind of what? Not water, obviously. You open your minuscule eyes, eager to see what that sea is made of, but the feeling immediately snaps away and again there is nothing around you. The impression is very strange indeed. A bit scary, even, but you are no coward and you quickly reason that just like so many other things in our universe, what you just felt is real, but invisible to the eye. So you close yours again, to enter the quantum world, yogi style. The sea is there, all around you. There are even currents? Yes. It seems so. Originating where the magnet is supposed to be and ending on the fridge. There are loops of force around and they flow right through you, and you realize that what you are sensing is what makes magnets and fridges interact. It is the so-called electromagnetic force field. Behind your closed mini eyes, it appears like a mist of strength that spreads all around, everywhere, a mist that is most dense next to the magnet and next to the fridge. Ripples are propagating through it, at the speed of light, telling you that the magnet and the fridge are moving closer to each other, meaning that they will sooner or later hit each other, meaning that. You open your eyes and stare in open-mouthed horror at the enormous black magnet that is about to crush you. You step back, shaking with fright. You are so close to the magnet now that you can almost see the atoms wiggling in its surface. There even seem to be tiny currents flowing within it. What are they made of? Are they electric? Magnetic? Both? You have no idea, but what is certain is that. Wait! What was that? Something happened. You saw it. It wasn't an arm reaching out from the magnet towards the fridge, but some light. Virtual or real, it is hard to say, but there was light. It popped out of nowhere, right in front of your mini eyes, from above the magnet's surface. Or was it from within? You turn your head towards where it went and you see the fridge's door, immense, moving towards you as well. You hold your mini breath. You are an instant away from getting crushed. More and more strange pearls of light appear from within the emptiness that seemed to separate the magnet and the fridge a moment ago, an emptiness that definitely does not look empty anymore. Pearls of light flash around you, exchange between the magnet and the fridge, like a host of tiny angels dragging the two objects towards one another. Mesmerized by the show, certain that your mini body is living its last moments, you wonder whether these particles of light are products of your imagination or real. They do seem virtual, for they last but an instant and appear out of nowhere, but they also have a very concrete effect on the magnet. Yes, these bright little fellows carry the force that brought the magnet close to the fridge in your house. You close your mini eyes. You are about to get crushed. But bing! You are back in your kitchen, staring blankly at the fridge's door, where the magnet just glued itself to the fridge with a tiny metallic sound. Wiping off a drop of cold sweat dangling on your forehead, you breathe, slightly embarrassed even though you're alone for having thought that it was anything but your imagination. It felt very real, though. You've just witnessed an action at a distance that is not due to magic, although I admit it is rather spooky. You've seen, beyond any doubt, that the mysterious force that makes two magnets interact, the electromagnetic force, was carried by virtual particles of light, particles so strange. They exist for one purpose only, to carry the electromagnetic force. They appeared in between the magnet and your fridge, out of what seemed to be nothing, but is not. You have just discovered that in between any two objects in the entire universe, whether magnets or not, there exists something that is called the electromagnetic field. A sea of force out of which virtual particles of light can pop at any moment. Right now, as you stare at your fridge, countless such virtual little pearls of light are exchanged between the magnet and the door, but you can't see them anymore and never will. That is why they are called virtual. They pop out of a void that is not a void, and disappear without allowing anyone to see them. Such virtual force carriers are everywhere around you, right now, and even inside you. They all belong to the electromagnetic field, an invisible mist that fills not just the space in between fridges and magnets, but the entire universe. What about magnets that repel each other? You've certainly seen that, haven't you? As you shall soon experience when flying through an atom, the virtual pearls of light you've just been introduced to can either attract, repel, or do nothing to the matter we are made of, to the matter that surrounds us. It all depends on what the matter in question contains. In fact, it so happens that it depends on one thing only, a thing that scientists have called the electromagnetic charge. And just as you can measure your mass on a weighing scale, you can measure your charge using an instrument, too. Yours, overall, is zero, though the human body is electromagnetically neutral. But that is not the case for the individual particles that make up your body. Only two types of electromagnetic charges can be found in nature. For convenience, they have been called positive and negative, plus or minus. But they could have been called anything, really. The rule is that virtual pearls of light repel like charges, whereas they attract opposite ones. Plus and plus, just like minus and minus, are pushed away from one another by the virtual light that appears between them. And the closer they are, the more the virtual pearls of light, the stronger the repelling force. Plus and minus, on the other hand, like to cuddle. Like your magnet and your fridge. And the closer they are, the stronger they attract each other. Neutral objects, on the other hand, don't care about these pearls of light, and one can be neutral either by having exactly as many positive and negative charges, or by carrying no electric charge at all. These are the rules of the electromagnetic field. Now, you may think that, since such an explanation of how magnets and fridges interact cannot be seen with our eyes, this may all be a very useful mental construction but not quite something that corresponds to how nature really works. The electromagnetic field, you may then argue, is but a picture that gives scientists a way to describe how charged objects react to a magnet's presence. A picture. A clever and imaginative one, for sure. But nothing more. You could think all this, obviously, but you would be wrong. The field you've just been introduced to, this invisible mist that permeates the entire universe and becomes somewhat more active near and in between charged objects, is much more than that. For one, it is very real. In fact, not only does it rule everything that has an electric or a magnetic charge, it is also the entity that gives birth, everywhere in the universe, to every and any electromagnetically charged particle, as well as to light. The electrons you will soon encounter are expressions of it. The light that your eyes detect is another. They are both but ripples in the field. Many amongst the brightest scientists on Earth today consider the electromagnetic field to be more fundamental than magnets themselves. Or even than fridges. More fundamental than light, even. And more fundamental than you. However absurd that last bit may sound. Before the end of this part, you will become aware of the existence of two other quantum fields that also fill the entire universe. And you will realize that, as far as modern science is concerned, you and I and all the matter we know and see and all the light that shines anywhere are all but expressions, ripples again, of these fields. We humans are indeed like fish in a sea. A sea made of fields. Just like everything else. And even though our ancestors once lived in the sea, it still took them eons to evolve and figure out the existence of quantum fields. 3. Entering the atom. You've been blankly staring at your tacky fridge magnet for long enough. You shake your head and open your fridge to pick up that milk you so badly wanted before the magnet drew your attention to a rather spooky phenomenon. Walking back to the table where you left your mug, you are about to pour the milk when the sight of the gold lying nearby makes you stop. What exactly are those atoms of gold that you found earlier, or the atoms wiggling on your magnet's surface? Are they like small, round balls? Are they cubes? What exactly are the charges that the virtual pearls of light from the electromagnetic field like to act upon? And what on earth did I mean by saying that they all are expressions of some fields? As you might have expected, these questions send you right back into your mini-you state, and you find yourself floating in the middle of the kitchen, far away from any familiar object, curious to see what this atom of gold you singled out earlier is made of. But it is not an atom of gold that you encounter first. Rather, it is the smallest atom there is. The one that makes up 74% of all the known matter in the universe, hydrogen. The very atom that stars like the sun fuse in their core to create bigger ones and, as a byproduct of this fusion, to shine. To be fair, however, you do not see much. There is something in front of you, of that you are certain, but you have a very hard time finding out where it is, not to mention what it is. Sharpening your mini eyes to focus even more closely makes no difference at all, so you decide again to try to feel it, yogi style. Amazingly, it works. Your eyes are closed, but you can picture something. Some kind of wave rippling the ambient electromagnetic field. A wave wiggling around a sphere. A hollow sphere, or a hollow lobe, rather. And it is not really a wave, in fact. But it looks like a spherical, no, lobe-shaped one, with ripples that move fast. At a speed very close to the speed of light, so that the world it sees must be very distorted, not to mention the way its time ticks compared to yours, but it isn't really focused in a particular position. Alright, let's be frank, you do not know what you are picturing, but this whole spherical, or lobe-shaped or whatever, fast-moving 28 thing does carry an electric charge. You can feel its effect on the background of the electromagnetic field, just like you did with the approaching magnet. Is that what an atom is? Still focused, you realize that there is something else. Something buried deep down, something very small compared to the volume spanned by the moving wave, but something that has to be strong, very strong even, to keep that moving charge you feel from wandering away. The hydrogen atom, you realize, has a core surrounded by a moving charge. All atoms in the universe have this structure, a core of varying size surrounded by one or more electrically charged waves. Scientists have called that core the atomic nucleus, while the fuzzy, charged, wiggling wave is an electron. And this is a puzzling revelation. The electron looks nothing like the tiny dot you had pictured it to be. To make sure you aren't getting this wrong, though, you quit your yogi mode and open your eyes. Rather unexpectedly, the wiggling wave immediately disappears, to become something else, something that looks much more like a particle. Good. Electrons exactly identical to this one are present in various numbers in all the atoms of the universe. They are the basis of all our electrical and magnetic devices, be it a computer, a washing machine, a cell phone, a light bulb. Anything. All our energy and communication tools depend on them. Slowly, very slowly, you therefore move one of your tiny hands forward to grab this one and study it up close. Strangely enough, the electron is very hard to catch. Every time you manage to spot it from the corner of your mini eyes, it starts moving erratically, as if the very act of your trying to locate it made it change its course in an unpredictable way. This is not your imagination playing a trick on you. It is a real phenomenon. One of many that occur in the quantum world but not in our everyday world of crystal vases and cups of coffee. It is part of a fundamental uncertainty of nature as it is seen from our point of view. You will have a deep look at what it means in part 6, but you already feel that there is something uncanny going on. What you need, you think, is to actually capture this electron and make it talk. That's right. Mini you or not, you are pure mind down here, you can do whatever you please. And you'll be damned if a tiny electron will prove you wrong, so hop. Faster than thought, as your mini eye catches a glimpse of it, right there, to your right, you pounce on it. And there it is now, in your right hand, which you keep tightly closed. The electron is wiggling inside, it feels as if a butterfly flying at nearly the speed of light is flapping its wings against your palm. You start to squeeze your fingers. Electrons are charged particles, they interact with the ones contained in your mini hand through virtual pearls of light popping out of the electromagnetic field. You squeeze, and squeeze, and squeeze, eager to have it quietened down within its tiniest of prisons, and suddenly, you don't feel it anymore. It is gone. You open your fist. No electron in there. You are absolutely certain that you did not leave any gaps between your tiny fingers, but still, it leaped out. And you felt nothing. It jumped through you, without touching you. It is back surrounding the invisible core of the hydrogen atom you had taken it away from. How rude. But how did it do that? How could the electron leave your grip without touching you? Well, it tunneled through your hand. It jumped. A record-breaking jump. A quantum jump. Something that is confined to the subatomic world and that doesn't exist in everyday life at the macro level of kitchens and vases and aeroplanes. Or so one might think. You haven't managed to analyze an electron yet, but you already know one of its weird properties: it can jump like nobody's business. The phenomenon itself is called quantum tunneling or quantum jumps, and it so happens that not just the electrons but all the particles you will find in the quantum world can quantum jump or tunnel like that. Now that we have established that, let's pause for a second to reflect together upon terminology. When scientists discover something new, they need to give it a name. For the very small, for the quantum world, they make up word associations where the word quantum is followed by another, usually from the vernacular. Here we have tunneling, or jump, or world, all terms that are easily understood and which, on their own, do mean what they mean for us in the everyday world. The presence of the word quantum, however, serves as a warning. Quantum means there is something fishy going on. In the example at hand, the fishy thing about quantum tunneling is this: electrons really do tunnel through things. But there is no tunnel. Quantum jumps hardly ever happen at the human scale, but imagine if they did. Imagine you are back in time, when you were a kid, in this very kitchen. Your father just asked you to clear the table, but it is late and you suddenly feel all of the 100 kilometers of air that weigh on your frail shoulders. You mumble something barely audible but not unlike a bear cub's growl. Nothing works though. The table is waiting for you. You sit down on the floor, full of despair. And there you go. You suddenly find yourself in the dining room, on the other side of the kitchen wall, near the table, and everything, all the cutlery, the plates and glasses, they all tunnel or jump or whatever right through the wall to the kitchen. This might sound like a fairy tale or a scene from Mary Poppins, but to be fair, with quantum jumps like this, there's no telling where the cutlery and dishes and glasses would jump to, so there's hardly any chance at all they'd end up in the dishwasher, and your father would have to buy everything again, for you'd never find any of them. Sounds strange, doesn't it? Well, that is quantum tunneling. Doors and walls and privacy would not exist were quantum laws to apply at our scale. Fortunately, and rather mysteriously, they don't. Thanks to quantum tunneling, however, almost everything in the realm of the very small can cross any barrier. How? It is understood that they can do so because they are allowed to borrow energy from the quantum field they belong to, the sea within which they swim, a sea that fills every single place in space-time. As much as they want. The dream of all athletes. But that doesn't tell you what an electron looks like, and I'd rather be quite honest with you, you may have to face a slight disappointment here. Picturing an electron is not going to be possible, because of the very quantum field it belongs to. The electromagnetic field is everywhere, and every single electron that exists in the universe not only belongs to it, but also is exactly identical to any other electron, anywhere and anywhen. Interchange two of them, and the universe won't notice. Because of that, because of the quantum field they are an expression of, electrons cannot be described as one would describe a macroscopic object. They belong to the field. They are part of it, like a drop of water in the vast ocean, or a gust of wind in the night air, a drop or a gust you cannot localize. As long as one does not look, drops and gusts are just like the ocean itself, like the wind. Mingled into an entity much vaster than themselves, they have no identity of their own. In the quantum world, as soon as you look, the electrons do become particles with given properties, like drops taken out of the ocean, but their properties are like nothing you've ever seen. They do not behave as expected, or at least as our senses might expect from our experience of everyday life. If you know where an electron is, you cannot know how fast it is moving. Its speed becomes unpredictable. That is why you had a hard time finding the electron around the hydrogen atom. Anytime you saw it, it started to move erratically. You were unable to follow it and it vanished from your sight. In a similar way, if you know how much energy an electron has, you cannot know how long it will keep it. Energy and time, position and velocity, are concepts that are not independent of each other down there within fields, in the quantum world. You will hear more about all this in part 6, but for now, since your mini-you is touring the quantum world for the first time, you can consider it a warning. Your mini-you should just take it all like you did as a young child discovering the world, without prejudice. Position and velocity cannot be known simultaneously? Fine. That's the way it is. Quantum laws allow for otherworldly jumps and tunneling? Okay. So be it. Interpretation will come in due course, or not. That being said, this whole quantum tunneling business does sound like utter nonsense to me as well, and I have been told that, after a course he gave on quantum physics, Einstein once said to his students, "If you have understood me, then I haven't been clear." So if it sounds like nonsense to you as well, everything is fine. Nature doesn't take offense. It is there for us to discover, and that's it. But is it truly real? Well, some people did take quantum tunneling very seriously and tried to find practical applications for it. Amazingly, they succeeded. About 30 years ago, working for IBM in Zurich, Switzerland, German physicist Gerd Binnig and Swiss physicist Heinrich Rohrer became convinced they could use quantum tunneling to browse any surface at a phenomenally small scale and see what the surface looked like. They believed quantum tunneling could allow them to actually see the atoms. Normally, an electron does not leave its atom if it has nowhere better to go. And normally, if there is somewhere else to go, it needs to be pretty close by, otherwise the electron can't get there. This is unless it uses its quantum power to tunnel through voids and jump over obstacles. With an extremely thin and sharper than sharp needle connected to an electric current detector, Binnig and Rohrer scanned the surface of a material without touching it. Being rather far from it, they shouldn't have detected anything, the distance between the surface and the needle being too great for an electron to cross. But they did detect electric currents, corresponding to electron jumps. 29, and the closer to an atom on the material's surface the needle was, the more jumps they detected, the greater the electric current. They then mapped these currents on a chart and they got a 3D picture of the material at an atomic level with extraordinary details. They had built a microscope, a scanning tunneling microscope, as it is now called, which could see the atoms themselves. Its precision is astounding, between 1 and 10% of the diameter of a hydrogen atom. In other words, if hydrogen atoms had feet, a scanning tunneling microscope would be able to count them, maybe even the number of toes. Atoms of gold like the ones you found in your kitchen were scanned this way decades ago, and scanning tunneling microscopes are today used to picture how different types of atoms are intertwined within the matter that surrounds us, as well as in state-of-the-art human-made materials. With such a microscope, engineers have gained the ability to move individual atoms around. Quantum tunneling is real. And it has practical applications. For designing such a tool, Binnig and Rohrer were awarded the 1986 Nobel Prize in Physics. 30. Electrons like the one you've tried to catch populate the outer reaches of all the atoms of the universe. And they are elusive. But despite being unable to describe exactly what they look like using the terminology of everyday life, scientists have learned to accept their strange behavior. As far as today's science knows, electrons are not made of any smaller particles. Unlike atoms, they cannot be cut, or split, or broken at all. They are just made out of the electromagnetic field, they are an expression of it. For being nothing but themselves, for being one of the most basic, fundamental expressions of the electromagnetic field, electrons are called fundamental particles. By contrast, the evanescent pearls of light that earlier appeared in between the magnets and your fridge were called virtual particles. These were force carriers. They existed only to carry the electromagnetic force between electrically or magnetically charged particles. Atoms, being made out of smaller constituents, are not fundamental particles. They are made out of many of them. Now, electrons do not just interact with the rest of the world through virtual photons. They can also play with real photons, with the real light your eyes detect. This game of matter and light is what makes us see the world as we do. As they are understood nowadays, real photons, like electrons, are also fundamental expressions of the electromagnetic field, made out of nothing else. They are pure ripples within an invisible sea, quantum ripples able to behave like waves and like particles. A bunch of them are now washing over your hydrogen atom. They traveled a long way to get there. For about 1 million years they fought their way from the sun's fusion core to its surface, which they reached about 8.5 minutes ago. Free, at last, to race through outer space unhindered by matter, they shot at the speed of light across the 150 million kilometers that separate our star's furious surface from our planet. Out of all the places they could have gone to, these photons ended up hitting Earth's atmosphere just a fraction of a second ago, only to charge through it and reach your kitchen window. From there wasn't much left for them to do. They went through the window pane and washed over your hydrogen atom. Your mini-you watches them as they stampede through the kitchen, hoping to see them hit your atom. Instead, they all fly through it and smash against your kitchen wall. Except one, which is gone. Vanished. Where did it go? You look around, surprised, until you realize that your hydrogen's elusive electron is now wiggling differently than before. Considered as a wave enclosing the nucleus, its crests are closer to one another. How can that be? It became excited. It swallowed the photon. Remember that we first met this strange phenomenon back in part 2 when checking the first cosmological principle, some time ago. But now something even more interesting is happening. After a short while, the electron suddenly spits out the exact same photon that disappeared, the photon it had swallowed, in a random direction. After taking a moment to ponder this, you draw the only possible conclusion, that the most well-known fundamental particles of the electromagnetic field, namely the electrons and the photons, can and do interact with each other. That electrons and photons can turn into one another. Mulling it over some more, you realize that you've actually always known it. Don't you feel warm when bathed in sunlight? Doesn't your skin heat up when, in wintertime, it faces a few burning logs in a hearth? Your skin, like all the matter in our world, is made of atoms whose outer layers are filled with electrons. When light from the sun hits them, the atoms of your skin and their electrons catch some photons that are turned into excited electrons that wiggle somewhat faster, creating the heat your body enjoys. It is such an incredible discovery that I here say it again, matter and light can, and do, turn into one another. Everything is a game of matter and light in this world of ours. But not only that. For the tough electron world. In the last 2 chapters, although you only saw a magnet interact with a fridge and skimmed the surface of an atom, you made great discoveries. You solved the mystery of electromagnetism's action at a distance and saw how matter and light can play with each other. Of course, this game is but one facet of our world, but it is a phenomenon that our humble human senses are built to be aware of. Light continuously hits our body, exciting electrons within our flesh, within our eyes and on our retinas, heating up the matter we are made of, giving it some energy. Atoms can also spit back the light their electrons swallowed, making us and objects shine with one or more colors, the colors of the atom or the set of atoms that swallowed them. That is what gives our eyes, our skin, our hair and clothes, all the plants and stones, a color, just as it gives faraway stars a particular hue as well. Light rays hit a tomato, all of the visible light is absorbed to heat it up or to be stored within, except for red light rays, which, serving no purpose for the tomato's atoms, are spat back out, off on their journey to tell our eyes that we are looking at a lovely red tomato. Without the electrons and photons, we wouldn't see a tomato or each other, nor would we know what the rest of our universe is made of, or that it obeys the same physical laws far away as the ones that apply around us. But what is even more amazing is that, thanks to our senses, our bodies transform all these otherworldly interactions into sensations processed by our brains. Thanks to that, mankind figured out the science behind those interactions, and the existence of fields that fill in the entire universe. And this is not just amazing, it's plain miraculous. Now what about that atomic core, the nucleus? Is it made out of electrons too? Is it yet another expression of the electromagnetic field? It has to be, in some way, for as far as you can tell, the whole hydrogen atom you are looking at is electrically neutral. The core must, then, have a charge too, opposite to that of the electron that surrounds it, so they both cancel each other out when seen from a distance. But how come you do not see it? As your tiny self scrutinizes the hydrogen atom that floats in the middle of your kitchen, it suddenly occurs to you that this hydrogen fellow looks awfully like a lot of empty space compared to what it actually contains, whatever its core may be made of. That fact, the amount of emptiness lying in between the core and the electrons, is actually shared by all the known atoms in the universe. Strange. Why, then, doesn't a magnet just cross through the surface of a fridge, the vast, empty spaces of the magnet's atoms wafting past the vast, empty spaces of those of the metal door? Why does it instead stay stuck to it? Shouldn't colliding atoms just not collide, and cross like two clouds of vapor, without even noticing each other's presence? Well, no. Fortunately. Or the world wouldn't be solid. And the electrons are the reason why, not the nuclei. To figure out what that reason is, the atom of gold you've already prepared will come in handy. The hydrogen atom you've looked at so far is the smallest atom there is. An atom of gold is bigger. You jump next to yours and look at it. The first thing you notice is that it does not have one lone, wavy electron whizzing around its nucleus, but 79, all 79 being identical to the lone, wavy electron whizzing around the hydrogen core. The second thing you notice is that, however identical they may all be to each other, these wavy electrons do not share their territory at all. Ever. They simply and plainly avoid being at the same place at the same time, because it so happens that nature forbids them from doing so. Whatever the atom they belong to, their wavy selves overlap nowhere, thus imposing very strict conditions on their potential cohabitation within any atom. They have no choice but to arrange themselves in layers, like an onion, around the nucleus, and that is exactly what they do. Only 2 electrons can fill the first, innermost layer. Only 8 can settle in the second, 18 in the third, 32 in the fourth, and so on. These numbers are known and they are the same for all the known atoms in the universe. What makes one atom different from another is linked to the number of electrons it contains, not to the nature of these electrons. Electrons are always identical. Hydrogen, the smallest of atoms, has 1 electron whose orbital lies within the first electronic shell. Helium has 2 electrons. Their orbitals fill up the first shell. Neon, to take a third atom at random, has 10 electrons. Its first 2 electronic shells are saturated. The chemical and mechanical properties of all the atoms are related to how full their external atomic shell is. If you want to add an extra electron to an atom, you can't just put it anywhere you please, and certainly not within an already filled layer. Now, were the electrons dot-like particles, that would be hard to conceive. But although they can indeed be like little marbles under some special circumstances, they also cannot be, so as to behave instead as waves. And waves can very easily fill in some volume. And that is how, on a filled electron layer, there's no space left for a newcomer whatsoever. Were an extra electron to really want to be part of an already built atom, it would either have to settle further away than the natives, where space might be available, or take the place of one that is already there, kicking it out. They just abhor having their wavy selves overlap. It's a dog-eat-dog world. This non-cohabitation rule has a name. It is called the Polyexclusion Principle. It was discovered in 1925 by Swiss theoretical physicist Wolfgang Pauli, 31, who was awarded the 1945 Nobel Prize in Physics for it. This exclusion principle is the reason why magnets stick to fridge doors without crossing them, or, perhaps more importantly, why you can't walk through walls, and why you don't fall through the floor. It also explains why you can hold this book in your hands. The atoms in its cover have outer electrons that absolutely refuse to give their place to the ones in your fingertips. And your electrons won't budge either. So they keep apart. And there's no way your own strength could force any of them to act otherwise. Electronic waves do not overlap. Ever. Don't try to run through a wall to prove me wrong. Your nose would break long before the electrons noticed anything. That being said, although electrons like their privacy, they do not mind being shared. And this allows them, rather fortunately for us, to build the matter we are made of, as you are now about to see. You were about to plunge into your atom of gold, but it will have to wait, for it so happens that an atom of oxygen is passing by. You stare at it. Smaller than gold, oxygen, with its 8 electrons, is still much bigger than hydrogen. Its first atomic shell is filled, but there is room for 2 more in its outermost shell, the second one, which has 6 electrons and could contain 8. The hydrogen atom's lone electrons are not about to let such an opportunity pass. And there are 2 hydrogen atoms nearby, so as soon as oxygen passes by, hop, the first hydrogen's lone electron jumps over and settles down within the oxygen's family, never to be alone again. And hop, just as you see it happening, the other hydrogen's electron fills in the last spot. And since all the electrons in the universe are exactly identical, no one can tell who was there in the first place and who arrived later. The perfect assimilation. Bound to their electrons by virtual pearls of light, the nuclei here have no choice but to follow them, and so the 3 atoms are now stuck to one another. 2 hydrogens and 1 oxygen are forced to cohabit. This done, there's no more space available for any extra electron. The whole construction is stable. By sharing their electrons as above, atoms become part of larger structures, which are called molecules. The molecule you've just seen being built is made of 2 atoms of hydrogen and 1 of oxygen. 2 HS and 1 O, HO. It is water, the most precious molecule for life as we know it. On a universal scale, water is not usually assembled in your kitchen, though, but rather in outer space, inside the huge clouds of stardust that are scattered within galaxies, and which astronomers call nebulae. Within these nebulae, the oxygen forged in exploded stars mixes with hydrogen, which can be found everywhere. When stars die, they send their seeds away, paving the way for water molecules to be built. And many other molecules as well. By sharing 1 or more of their electrons, many atoms can be bound together, in many different ways, to form chains of various complexity. Nature has built molecules of different sizes and properties this way, from rather tiny ones to extraordinarily long ones, such as your own DNA, which, with its billions of joined atoms, carries all the information needed to build someone like you. It is to shed some light on the genesis of these molecules that started life on Earth, and to unravel the mystery of the origin of the water that today covers 70% of our planet's surface that, within the last decade, many satellites have been sent to outer space. Does our water come from asteroids that struck our planet some 4 billion years ago? Or from comets that did the same? And did these rocks and ice balls carry some, or all, of the molecular seeds of life? We should soon know, for many of these satellites are now on site, or on their way there. In the meantime, we do know one thing, however, only 6 atoms were necessary to build all the molecules required for life to thrive on Earth: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. The so-called CHNOPs. Incidentally, since your whole body is made out of molecules that are made out of these atoms, assembled in various ways, you are a CHNOPs. No offense meant at all. Now, as you contemplate your CHNOPsy body, another question pops up in your mind. Since both you and the air are made out of these atoms sharing their electrons, how is it, then, that you can walk through air but can't walk through a wall? An important question indeed. As far as we know, air is filled with atoms, which have as many electrons as one could want, so they shouldn't let you pass. No. That's Pauli's rule. The answer is that the atoms in the air are not all sharing their electrons and hence don't hold onto each other that much, whereas, forming a solid, yours are. Instead of stopping you from moving at all, the electrons that surround the atoms that make up air move away as yours force their way through, incidentally bumping into each other, creating some wind. That, incidentally again, is the difference between a gas and a solid. In liquids, nearby atoms are a little more tightly bound to each other, but not enough to stop you, unless you try and enter too fast, like when diving off a cliff into the iron-gray sea. In solids, atoms don't move aside unless you force them hard to do so. Think of sharp scissors cutting through paper. Now, instead of fighting for its position, an electron can also be forced to leave, offering an empty spot for another electron to fill. When an atom loses an electron, the combined charges of the core and the electron do not add up to 0 anymore. Atoms stripped of one or more electrons become what scientists call ions. 32 ions tend to look for something to bond to form a molecule. In fact, they're desperate to find electrons. In the terminology of physics, they are fiercely reactive. Conversely, bonds created by electrons within a molecule can also be broken. Energy is usually released during such a process, and that is what eating food is good for. Chemical reactions inside your body break up the molecules contained within the food, releasing energy that is then used in many ways by your organism to keep you alive. All right. This wraps up our survey of the electron's tiny world. You've only skimmed the outer part of 3 atoms, and yet you've already figured out how modern science understands pretty much everything our bodies experience on a daily basis. So, before heading for the still mysterious atomic core, I shall summarize for you what you've been through over the last couple of chapters. The outer parts of all the atoms throughout the universe are smeared out, wavy, massive electric charges called electrons. They are fundamental particles of the electromagnetic field, and they are very protective of their personal space. The Polyexclusion Principle forbids any 2 electrons from being at the same place in space and time. Even though there is more void than anything else in all the atoms of the universe, that is the reason why you cannot walk through a wall, do not fall through a chair, or through a bed, or through pretty much anything solid. Living would be tricky otherwise. Pauli's rule also brings about the structural and chemical differences between different atoms. Since electrons cannot all crowd as close to the nucleus as is possible, they occupy a series of onion-like layers around the atomic core, filling available spaces only, making the atoms grow with the number of electrons they contain. Electrons, it has to be said, are not the only particles subjected to Pauli's exclusion principle. Other particles are, too, but not all. Light, for instance, begs to differ. You can pile up as many photons as you want in as small a place as you want. They won't mind. In fact, they quite like it, and the more similar two photons are, the more they tend to cuddle each other, like penguins in the cold. Lasers are a consequence of such fondness. They are highly concentrated, highly energetic beams of identical photons. Now, having got this far, you might be left with the impression that electrons and light are the only particles that count in our universe. But that is not true. You will soon see that there are others within atomic nuclei, but I just want to stress that there are even particles around us that care neither about the electron's wish for privacy, nor about their existence at all. Or about anything else we know, for that matter. They are particles that do not belong to atoms. Some of them are actually so aloof that most of the time they shoot through anything and everything, leaving barely a trace of their passing. For these tiny particles, the universe must seem pretty dull and empty. Even Earth. Even you. You'll meet them soon enough. For now, however, you should celebrate again. With what you've just learned about electrons and light, you know what only a handful of people knew half a century ago, and most of them were rather bright, since they got a Nobel Prize for figuring it out. But there is more. Thanks to them, you can now explain pretty much everything that happens around you, from the color of a tomato to the solidity of a wall or ground to the reason why magnets jump from your fingers to stick to fridges' doors. Everything you and I and all our friends experience on a daily basis is regulated by matter and light playing with each other, turning into one another, and by electrons categorically refusing to share their bit of space-time with a copy of themselves. The next time you embrace someone, feel free to imagine virtual pearls of light being created and becoming frantic as you get closer and closer to each other, before the electrons abide by Pauli's rule and decide that no, you cannot get any closer. I'm not sure you should talk about this amazing fact on a first date, but I leave that decision to you. Before you continue your journey through the matter we know, here is another good piece of news. In 2014, experiments done in the impressive underground scientific laboratories of the European Centre for Nuclear Research underneath the French-Swiss border confirmed that humanity had theoretically discovered everything there is to know about the matter we are made of. Everything. This does not mean there are no mysteries left. But it does mean that, since 2014, we have a picture of our universe's known contents that corresponds to pretty much everything we could possibly probe or find within the range of modern technology. That picture includes atomic nuclei, the atomic cores you are now ready to go examine. And if you somehow have a hunch that you will again find weird things down there, you are absolutely right. 5. A peculiar jail. Your coffee is getting colder and colder and your arm, holding the milk, aches. But you don't care. Your mini-you just decided to dive deeper and deeper within one of the hydrogen atoms that formed the water molecule right in front of your eyes, towards its core. Many evanescent pearls of light are appearing and disappearing all around you, confirming that the core you are aiming for is electrically charged, destroying the idea that there is only nothingness between an atom's electrons and its core. Still, compared to the size you guess the atom to have, you cross immense distances before reaching the hydrogen core. But you eventually find it. Like the electron spinning around it, the core of the hydrogen atom does not seem to have a particular shape, yet it does have a mass. But it is heavier. Much heavier than the electron, 1,836 times so. And it does have a charge, indeed the exact opposite of the electron's charge. It is called a proton. It is bigger than the electron, but compared to the size of the atom itself, it is extraordinarily tiny. New Zealand-born British physicist Ernest Rutherford discovered its existence in 1911, 3 years after being awarded a Nobel Prize in chemistry for his work on a then very new phenomenon called radioactivity. What he did not know, however, what he could not know, is that unlike the electron, the proton is not a fundamental particle. It has a world within. Not to waste time attempting the impossible, you close your eyes and spread your arms to feel, yogi style, what that proton's inner world is about. Immediately overwhelmed by a force so strong that anything you've experienced so far feels like child's play, you open your eyes again straight away. Electromagnetism can easily overpower you. Some magnets are so firmly stuck to each other you'd never be able to move one away from the other. Gravitation can also overpower you, and it actually does. You'll never be able to jump free of Earth's gravity. But this is another level of power altogether. Within the proton, within what looked like a fuzzy, cloudy sphere, you glimpsed countless virtual particles appearing and disappearing, like the electromagnetic pearls of light you saw between the magnet and the fridge, or between the electron and the proton. But these are not virtual photons. They are the carriers of a new force, and that force, together with the quantum field it belongs to, is the one that stabilizes all the matter in the universe. Without it, everything we know would disappear in a snap of the fingers. Everything. Your body included. The virtual particles that carry this amazing force, the force that keeps matter intact, are hundreds of times more powerful than the photons carrying the electromagnetic force. They are the force carriers of the so-called strong interactions. But if these were just the force carriers, why didn't you see the fundamental particles of that new field? Virtual photons made charged particles interact, so what is it that interacts here? Without any second thoughts, you jump inside the proton, close your mini eyes again, raise your mini hands, and probe. Feel. Search for the purpose of carriers of such a strong force. Surrounded by so much energy, a huge effort of concentration is necessary, but eventually you manage it. You can make out three things, three fuzzy, wavy, heavy little things that scientists have called quarks. The name may sound strange, but don't all names before we become used to them? No one, besides you right now, has ever actually seen a quark on its own. They do not even exist on their own. The strong, virtual little fellows that continuously appear and disappear around them just won't let that happen. The further apart the quarks are, the more ferocious the strong force carriers become, bringing them back close to one another much more efficiently than any other known force in nature. For the three quarks that live inside the proton, life is therefore rather confined. Jail-like, really. And their virtual prison guards, the strong force carriers? Who are they? What are they? They are not photons, that is for sure. They are not part of the electromagnetic field. Remember, they are expressions of another field entirely, the strong interaction quantum field. And they are so efficient at their job of gluing the quarks together that they have been called the gluons. Quarks and gluons. They make up all the protons of our universe. Now here is something strange about this tiniest of jails your mini-self is visiting. Most of us definitely believe that if you find yourself behind bars, as a person, then freedom means being as far away from your cell and its guards as possible. Well, for the quarks held in the protons, felons or not, it is the other way round. For them, freedom lies in short distances. The closer they get to one another, the freer they get to do whatever they want. Quark freedom is a very strange concept indeed. A world of possibilities opens up for them as soon as they get closer to one another. For having discovered this peculiar type of freedom, 3 American scientists, David Gross, Frank Wilczek and David Pulitzer, received the 2004 Nobel Prize in Physics. A hard concept indeed. So hard that when I met David Gross and Frank Wilczek in Cambridge, a couple of years before they received the prize, I remember wondering whether I should ask them to pay me back the money I spent on headache tablets trying to understand their work. Quarks and gluons. Elementary quarks, made out of nothing but themselves. And gluons. The carriers of the strongest force we know, the strong nuclear force, which keeps quarks confined, only allowing them to be free when they are holding close to one another, thus guaranteeing that the matter we are made of does not split apart. Quarks and gluons. Strange names indeed, names used to describe the essence of a reality so far from our daily lives that it may well sound rather insignificant. The The strong force, however, with its quarks and gluons, involves about 99.97% of the mass that makes up our bodies. Were a 60-kilogram person to lose all his or her quarks and their binding gluons right now, he or she would instantaneously slim down to weighing 18 grams and be dead, obviously. To understand what mankind has so far discovered about our reality, to even figure out what our reality is made of, quarks and gluons are therefore very necessary. And that, it seems to me, is a fairly good reason to study them. Notwithstanding the fact that they will shortly allow us to travel back to about a second after the birth of space and time. Now, as we have already said, the field these new fellows belong to is called the strong interaction field, or strong field. It is a quantum field, of course, so most of the weird quantum behavior found earlier, involving electrons and light disappearing and appearing elsewhere, or tunneling, for instance, does apply here as well. But what is important to underline here is that the strong field is not the same as the electromagnetic field, and yet it also fills the entire universe. It is another sea, if you will, whose drops are quarks and gluons rather than electrons and photons. And nothing prevents particles from belonging to both. Being electrically charged, the quarks belong to the electromagnetic field as well as to the strong interaction one. They can interact with the force carriers of either, through light and gluons. But over short distances, the gluons are much, much more powerful than light. Now, what about this new sea? What are its fundamental particles? The strong field has 6 of them, 6 different quarks which can pop out of the strong field anytime, anywhere, if sufficient energy is present. Only 2 of them are found within an atom's core, though. They are the so-called up and down quarks. There are 2 up quarks and 1 down in every proton in the universe, so it is fair to say that protons have more ups than downs, which perhaps explains why they are happy in their subatomic jail. But protons are not the only quark jails that exist, as you will now see within your atom of gold. Bored with the hydrogen, your mini-you jumps back to above the kitchen table where you cut your treasure to bits. Your atom of gold is still there, you dive into it. Buried deep beneath the 79 electrons that swirl around it, its nucleus is much, much bigger than the hydrogen atoms. To match the charge of its 79 electrons, you find 79 protons. But there are also other fuzzy spheres surrounding, separating these protons. Uncharged spheres. You can count 118 of them. Being electrically neutral, they are called neutrons. They, too, are quark jails, and they were discovered by the English physicist Sir James Chadwick, who happened to be a deputy of the extraordinary Rutherford. 33 Chadwick received the 1935 Nobel Prize in Physics for his discovery. Within every proton, gluons can find 2 up quarks and 1 down. Ups have the majority. Within neutrons, it is the other way round, downs lead 2 to 1. Now, how do all these jails stack up to make an atomic nucleus? Why don't they move apart from each other? Or collapse? The protons are all positively charged, after all. They should repel each other. But they don't. Why? Because the strong field and its force carriers prevent them from doing so, albeit in a very strange way. A residual way. To figure out what this means, your mini-you boldly decides to closely watch the elusive gluons that guard the quarks within a proton. They are there. You can't really see them, but you can feel them in yogi mode. They appear and disappear to keep the quarks from wandering away on their own. But suddenly, something very strange happens. Something has left. Something has jumped out of the proton. But what was it? A gluon? Why not, after all? They are guardians, not prisoners. But no, it wasn't one gluon. Not one on its own, anyway. You sharpen your yogi sense. And there you go. The gluons, it so happens, don't leave on their own at all. They have to find another gluon to pair with. A friend. Pairing with the right one, they turn into something else. You look around and right there, to your left, in between two quarks, it is happening again. A gluon pops out of the background field and so does a friend of his, another gluon, and they now stick to each other and pop. Just as light can be transformed into an electron, these two gluons transform themselves into two quarks. A quark duet that is not bound to the other quarks by the gluons anymore. They become free, as a new entity, to leave the quark jail they belong to. You watch them leave. They are heading straight towards a nearby quark jail. They have in fact become the carrier of yet another force, a force that acts not upon quarks, but upon the quark jails themselves. As they reach one, they transform back into gluons and start guarding the quarks there. It is thanks to such exchanges that neutrons and protons coexist within atomic cores. By traveling from one jail to another, two gluons turned quarks make sure that atomic nuclei remain stable. The exchanged particle, the quark duet that travels between jails, is called a meson. And the force it carries is called the strong nuclear force. It is an attractive force. And a very strong one. For having predicted the existence of mesons long before they were found in experiments, Japanese theoretical physicist Hideki Yukawa was awarded the 1949 Nobel Prize in Physics. In a funny twist, the boiling soup of quarks and gluons that can be found inside all protons and neutrons happens to also be responsible for the missing mass we mentioned a long time ago, the missing mass that makes stars shine. 34. Within stars, as you now well know, small atoms are fused together to build new, bigger ones. This means that stars fuse neutrons and protons together, and it so happens that once fused, these neutrons and protons do not need as many virtual gluons to guard their quarks as they did when on their own. It is a bit like when two companies fuse, some people are made redundant, and they are fired. In star cores, the redundant gluons and quarks and mesons are also fired. Because they carry some energy and because energy is mass, firing them lowers the mass of the newly fused core. That is why all cores built by fusion are less heavy than the fused ones taken separately. As opposed to people who have been fired, however, this missing mass is turned into energy, the exchange rate being given by E equals mc, making stars shine. Deep inside stars, gravitational energy is thus used to forge atoms, a process that also involves mass being transformed into light and heat and many other particles that are around but which our eyes do not see. Although most of our reality is hidden to our senses, everything is linked in this universe of ours. 6. The last force. So far, you've become aware of the existence of two quantum fields, namely the one responsible for all electromagnetic interactions and the one that gives rise to the strongest force known to mankind, the rather appropriately named strong interaction, with its residual strong nuclear force. In a sense, these forces, and their fields, are powers of construction. Even though magnets can either attract or repel each other, the electromagnetic force makes sure that the electrons stay around atomic cores. The electrons could move away, or collapse on the nucleus. They don't. Virtual pearls of light prevent them from doing so. The electromagnetic field gives the atoms their electronic stability and ways to share their charges, to build up molecules, to build up the matter we are made of. The strong nuclear force, on the other hand, is in the care of the atomic cores themselves. It keeps neutrons and protons together, building atomic nuclei. Without it, all nuclei would break apart and we would all instantaneously turn into a mist of protons and neutrons. And so would Earth and everything else. And to root all this, the strong interaction keeps the quarks confined within these protons and neutrons, binding them with gluons popping out of the background. So, you've traveled inside these two fields, you've seen that their interacting particles and force carriers give the world its hard, although elusive, tangibility. You've seen photons and electrons play with each other and turn into one another. You've seen gluons and quarks all wiggling within the cores of precious gold atoms and those of common hydrogen, the smallest and most abundant brick of matter in the universe, the one that stars fuse in their hearts to forge the substance you and I are made of. Hydrogen, whose exhaustion sooner or later triggers the death of all the stars in the universe. Pondering this last remark, you suddenly remember what will happen to our sun 5 billion years from now, and you immediately recover your normal size, leaving your mini-you floating somewhere else, in a world too small for your normal eyes to see. Your perception of the universe has changed hugely since you were lazily looking at the stars from the comfort of your tropical island beach. You now know that nothing is empty, that everything interacts with everything, all the way to the innermost parts of the atoms which were built out of and remain whole thanks to extraordinarily remote interactions. The sky outside your kitchen window is now turning red. The sun is setting somewhere to the west, illuminating the flat base of the clouds with fiery colors. Your arm aches for having held the milk for so long, but as you now sip your cup of white coffee, you mindlessly walk a couple of steps to stand next to the window and stare outside at the sky, and you suddenly better understand what it means to be part of a star's family. All the stars throughout the universe radiate and shower their surroundings with light and particles, all direct or indirect byproducts of their atomic nuclei fusion power plant of a heart. And whereas their gravity, the curve they create in space-time, makes every single close by or passing object fall towards them, these winds of particles and light are blowing outward, spaceward, towards the faraway, radiating ripples of invisible background fields that fill in everything. The universe really is like a vast ocean, and it so happens that some space engineers have imagined building spaceships with huge sails to capture these solar winds and propel their ships towards the outer universe, like cosmic sailors riding the slopes of space-time without needing any fuel. Night has now settled down and you haven't moved. The sky has cleared. You are staring at the stars. There aren't many, though. Light pollution is far too bright. Still, you now know the stars you would otherwise see from here are not the same as the ones you saw from your tropical island. You are now collecting photons emitted by stars dwelling in a different part of the Milky Way. But they are stars all right, huge balls whose gravitational energy is building large atoms out of small ones, merging their cores together. Quite remarkably, and rather contrary to what we humans are used to, everything seems to be a force of construction out there. Seems, yes, for you haven't yet seen everything that is known. For that, a third quantum field is needed. A third sea that fills in the entire universe just like the other two, a sea whose fundamental force carriers are neither photons nor gluons nor mesons. And this one can somehow be viewed as a field of destruction, a field that undoes what the others have done. It is the last of the four forces that rule our universe. This last force is also a nuclear force. Just like the strong one you've just discovered, it only acts upon the constituents of atomic cores. But this one is much weaker than the strong force, and it has therefore been called the weak nuclear force. The ubiquitous quantum field out of which its fundamental particles and force carriers are built is called the weak nuclear quantum field. The spontaneous splitting of atomic cores, a process known as radioactivity, is one of its attributes. Now, before you witness radioactivity in action, it may be worthwhile for you to recall that radioactivity has claimed the lives of many of its discoverers. Unaware that lethal invisible lights that slowly shattered their bodies were irradiating them, they processed raw, highly radioactive materials with their bare hands. The amazing Polish-born French scientist Marie Curie, the only person ever to be awarded a Nobel Prize in physics and a Nobel Prize in chemistry, was one of them. She may not have known why she died, but what you are about to witness is what she would have seen had she the knowledge we have today, together with the handy ability to turn herself into a mini Marie. As you empty your cold coffee into your sink, your mind shrinks back into your mini self and your mini eyes take a moment to adapt to the darkness. You are back near your atom of gold. It is right in front of you, an atom so strong and solid that an energy greater than that of a star's gravity is needed to forge it. Gold is not built during a star's life, but during its explosive death. When our sun dies, it too will create some gold, which, who knows, may one day be paraded on the finger of a future alien species. As you look at it, however, this atom of gold doesn't look nearly as valuable as pretty much all of mankind seems to believe. Why is it so coveted, then? Does it change as time passes? Does it catch passing atoms to build extraordinary molecules? You wait a bit to see if it is so. But no. Nothing happens. And there you go. The fact that nothing ever happens to it is one of the reasons gold is so valuable. Gold does not rust. It does not oxidize. It does not corrode. And when you have a nice lump of it, it is the most ductile of all metals. You can draw gold out into the longest, thinnest wire of them all. Put many gold atoms together and you can also easily mold the lot into pretty much any shape you like. And whatever you do to it, it will still conduct electricity, meaning that an electron introduced on one side of a long chain of gold atoms will wave its way along the chain and exit it from the other side. All these exceptional properties can lead to practical applications that may not always be very apparent in a wedding ring, but which are priceless. Add to this the fact that gold is rare, hard to mine and forged by the death of a star, and one understands why it is expensive. We'll leave it there, however, because nothing is happening to it at all, really. To see something different, you'd need another atom, and funnily enough, one is dropping by. And it is bigger. As far as you can tell, it has 94 electrons swirling around a core made out of 94 protons and 145 neutrons. 239 quark joules. That's 42 more than gold. This atom is one form of the infamous element called plutonium. And because it has 239 quark joules, it is called plutonium-239. There are other types of plutonium, just like there are other types of gold-35 besides the one you've found in your kitchen. These can have more, or fewer, neutrons in their cores, but they always have the exact same number of protons, or they would not be plutonium or gold anymore. And whereas gold wasn't very interesting to watch, something tells you that a strange phenomenon is about to happen, spontaneously, inside the nucleus of plutonium-239. Without any hesitation, you travel through layer after layer of its electron shells. You traverse huge voids filled with virtual photons. And then there is the nucleus. The 239 quark joules are right in front of you. The strong nuclear force is keeping them neatly stacked, but your gut tells you to aim for one of the neutrons. You plunge right in. There are 2 down quarks and 1 up quark in there, tightly kept together by the sturdy gluons. Just as you settle down, however, one of the down quarks is hit by a virtual particle you have not seen before, a virtual particle that spontaneously appeared only to transform your down quark into an up one. The neutron it belonged to thus just turned into a proton, creating havoc. Now the whole atomic core is out of equilibrium. The effect is instantaneous and dramatic. A sixth sense tells you to run for cover and your mini-you rushes out of the core and the electron layers only to see the plutonium nucleus split and split and split again into other, smaller ones, all of them trying but sometimes failing to take some electrons with them. Extremely energetic particles are fired off at each stage of the process, including yet another one which you have never seen before. Your plutonium is decaying. Right in front of you. And all the products of this decay are now shooting away. A firework that eventually burns itself out. Unless many other plutonium-239 atoms are around. But there aren't, in your kitchen. So everything quickly quietens down. You just witnessed one aspect of the fourth known force of nature, the weak nuclear force, with its virtual force carriers that can turn quarks into one another. These force carriers are called the W and the Z bosons. What you have just seen is the decay of an atom into smaller, more stable ones. It was the spontaneous fission of an atomic core, the very opposite of its fusion. A radioactive decay. This is what radioactivity is all about, and the weak nuclear force is in charge of it, with its W and Z bosons to carry it. Wolfgang Pauli, the same Pauli who came up with the exclusion principle, studied such atomic decay about 100 years ago. He didn't know about fields, as you now do, but when comparing what he observed before and after a radioactive decay, he realized that there was some energy missing. So he forecast the existence of a hitherto unknown particle that could be blamed for carrying that energy away, a particle with minute mass, a particle carrying no electric charge whatsoever, a particle so elusive that, once it has been fired, shoots through all the matter we know almost unhindered. This new particle is now known to exist. You just saw it. Out of all the particles fired out by the radioactive decay, it is the one you had not seen before. It is called a neutrino. U.S. physicist Frederick Raines and his colleagues detected it experimentally in 1956, and Raines received the Nobel Prize in Chemistry for it almost 40 years later, in 1995. As he once said, neutrinos are the tiniest quantity of reality ever imagined by a human being. Today, we know that these neutrinos are only subjected to the weak nuclear field and gravity. They are entirely unresponsive to the electromagnetic and strong fields. For them, atoms really are what they look like to you in the first place, empty. And that is a good thing. Why? Because were the neutrinos to interact with atoms, we would be in trouble, for they are abundantly produced within the Sun, very abundantly, in fact. About 60 billion neutrinos shoot through every square centimeter of your skin. Every second. And they don't even notice you. Not a single one of them. However vexing it may sound, they can't tell the difference between you and, say, nothing. They shoot through you. And then through the Earth. 36, and they continue their journey spaceward, as if neither you nor our planet had ever been there in the first place. Now, we've all been taught that radioactivity is dangerous, and that one should, as much as possible, run away from radioactive materials like plutonium or uranium or radium or polonium. And rightly so. But since the neutrinos can't really tell the difference between you and nothing, they can't be the reason for this danger. The reason has to do with the other particles fired during a radioactive decay, and luckily enough, you are already familiar with them. When the core of an atom decays, it splits and can emit neutrinos and quark gels and electrons and light. And the last three are dangerous. The largest of these consists of 4 quark gels bound to each other, 2 neutrons and 2 protons stuck into a lump. It is called an alpha particle and actually corresponds to an atom of helium that has been stripped of its electrons. To become an atom, that core therefore needs to steal 2 electrons from somewhere else, a feat it can achieve in several ways. It can strip some out of nearby atoms, it can share some with nearby atoms, or it can adopt wandering ones. In the first case, the atom stripped from its electrons starts to look for other electrons itself. When there are living creatures nearby, weird chemistry can happen with electrons being stolen from atoms on the skin, leading to what is called radioactive burns. That's why alpha particles are dangerous. The second type of particle that can be fired by an instance of radioactive decay is a very energetic electron, which can knock off other electrons far away, while the third type is a very energetic photon, a gamma ray. We met them on our earlier journey through the cosmos, remarking on their incredibly high energetic frequency. A gamma ray can, just by hitting an atom, strip it of one of its electrons, turning that atom into an ion eager to find another electron, creating burns on our skin again. But gamma rays can also do much worse. Nothing obliges them to stop at the surface of our body. They can penetrate it and cause local havoc deep inside, not just by kicking electrons out of their atomic home, but also by breaking molecules, like DNA molecules, in the heart of our cells, thereby changing the instructions used by our organisms to create everything our bodies need to live. The outcome usually is cancer and/or genetic mutations. All these potential outcomes are scary. There's no way one could argue otherwise. But there is a bright side too. Just like gravity and electromagnetism and the strong interaction, radioactivity, despite being a force of destruction, is a natural process that occurs all the time everywhere, even within your body, at a very slow rate. Only if one is exposed to high levels of radiation should one worry. In fact, everyone should be very grateful radioactivity exists at all. It can kill you, yes, but without it you wouldn't have been born in the first place. On Earth, deep under your feet, our planet happens to contain many atoms that do decay, all the time. Less so now than in the past, but still, Earth's mantle is radioactive. When atoms decay there, the particles they emit bump into their neighbors and generate heat, the very heat that contributes to keeping our planet warm. Without radioactivity, there would be no seismic or volcanic activity. The surface of the Earth would have been dead cold billions of years ago. Life as we know it would probably not exist at all. Radioactivity breaks the atoms. Radioactivity kills. But it is needed to heat up our world, giving us back some of the energy that stars stored within the atoms that built our home planet. Now a last little comment before letting you embark on a journey towards the origins of space and time. Atomic energy as a whole, through fission or fusion of atomic cores, involves extreme energies, and these energies are what mankind tries to harvest, with more or less efficiency, within nuclear power plants. We can only hope that such technologies will one day become clean and safe, for their potentials are astonishing. Despite their having a rather bad press, and despite their past unjustifiable use, we should never forget that without nuclear forces, we wouldn't exist. Without radioactivity, life on Earth would be impossible. Life as we know it, that is, of course. Part 5. To the origin of space and time. 1. To be confident. When I started to be interested in what some might call hardcore theoretical physics, I was about 22. I had studied pure mathematics for some years before and was very fond of its beauty. As the Greek philosopher Plato said about 25 centuries ago, when no one had a clue what the heavens were about, mathematics is the language in which gods speak to people. When my application to study advanced mathematics and theoretical physics at Cambridge University, England, was accepted, I immediately thought, great. Time for some deep thinking about the real world. Little did I know what was about to happen to me, just as you possibly don't have a clue what is about to happen to you in the coming chapters. During the summer that preceded my first year at Cambridge, I read a few textbooks as well as works by the masters of the past and present, to get a clearer feeling for what science might have to say about the world around us. I concentrated especially on the quantum world. After all, as we found out in Part 4, the world of the very small lies at the root of everything we are. It is there that we find the building blocks of all that our universe contains. Indeed, to even use Einstein's general theory of relativity, one needs an understanding of what our universe contains, or its equations won't tell us what our universe looks like at large scales. Many Nobel Prizes in physics have been awarded to scientists for breakthroughs regarding the very small. Needless to say, I was very excited about the journey I was about to go on, and as I began to get to grips with the theories of these intellectual pioneers, I started to write down some of their incredible thoughts, to make sure I was getting it right. I think I can safely say that nobody understands quantum mechanics. Richard Feynman, Nobel Prize laureate for physics in 1965. The Lord God is subtle, but he is not malicious. Albert Einstein, Nobel Prize laureate for physics in 1921. No language which lends itself to visualizability can describe quantum jumps. Max Born, Nobel Prize laureate for physics in 1954. Those who are not shocked when they first come across quantum theory cannot possibly have understood it. Niels Bohr, Nobel Prize laureate for physics in 1922. I have second thoughts. Maybe God is malicious. Albert Einstein. Such statements, from the founding fathers of the field, would be enough to shake the belief of even the most confident of students. Still, alongside 200 other young men and women from around the globe, I sat through mind-boggling lectures and passed what was at the time called the Part 3 exam of the mathematical tripos, arguably the oldest maths exam in the world. It still consisted mostly of pure mathematics, and the amount of new material we learnt was so great that we had little time to really think about the philosophy of it all. And then came the plunge. 9 months after my arrival at Cambridge, Professor Stephen Hawking, one of the most famous physicists of our time, offered me the chance to become his PhD graduate student to work on black holes and the origins of our universe. Deep thinking was about to become compulsory. So I spent the following summer having another look at everything I could find out about, well, everything, and I reached pretty much the point you've arrived at now in the book. With Hawking as a supervisor, I was about to put it all together and to reach much, much further. Now it's your turn to do the same. What is there left to see? Well, here is a teaser. In 1979, a very special Nobel Prize in Physics was awarded to 3 theoretical scientists, Sheldon Lee Glashow from the U.S., Abdus Salam from Pakistan and Steven Weinberg from the U.S. For years, scientists had been trying to understand some rather peculiar aspects of the weak nuclear force that you recently saw in action. And Glashow, Salam and Weinberg discovered something incredible, that electromagnetism and the weak force are but 2 aspects of another force, another field, that existed a long time ago. They found that during the early days of our universe, at least 2 of the invisible quantum seas that fill our reality were once just one, the so-called electroweak field. This was an extraordinary breakthrough in its own right, but it also paved the way for something much, much bigger, the tantalizing prospect of unifying all the known forces of nature into just one force. The quest for such a unification lies behind everything you'll experience between now and the end of this book. With this goal in mind, you will travel towards the origin of space and time, within a black hole, and even outside our universe. In order to get there, however, you will first need to figure out what is left when one empties a place of everything it contains. To no such thing as nothing. You are still in your kitchen. The night is dark and quiet. If you thought that the world was beautiful before, it is now utterly transformed by what you have learned on your travels. Everything seems somehow deeper, charged with power and mystery. Even your humble kitchen. The air around you is filled with floating atoms, sliding down the Earth's space-time curve. Atoms first assembled in the cores of long-dead stars. Atoms within you, everywhere, disintegrating in radioactive decays. Beneath your feet, the floor whose electrons refuse to let yours pass, thus making you able to stand and walk and run. Earth, your planet, a lump of matter made out of the 3 quantum fields known to mankind, held together by gravity, the so-called fourth force, floating within and through space-time. This all sounds so absurd, or plain miraculous, that you decide to brew yourself some more coffee and make your way to the living room and sit down in your cozy, solid, reassuring old sofa. You try to bring some order to all these thoughts that are bumping around in your mind. Is the meaning of life hidden somewhere out there, beyond what we have already seen together? And indeed, does what you've learned so far actually make any sense? Before you head off to places even more remote than those you've seen so far, let me say this: unraveling the mysteries of the world is a work in progress. Science may not have all the answers, although it has many. It depends what your expectations are, in truth, for I must warn you now that the end may not make any more sense than the beginning. As U.S. theoretical physicist Edward Witten once said, away from the safety of your home, the universe was not made for your convenience. 37. It is probably worth keeping that in mind as we cast off into altogether darker seas, because however humbling such a statement may be, it offers us all the extraordinary freedom to interpret what we see in a personal way. And that is a good thing. For the more different points of view there are, the better for humanity, and the better for science. Now, as I hinted at the end of the last chapter, before we push confidently through the doors of the unknown, we first need to become comfortable with a concept that scientists have called the vacuum. It is the basis of how our quantum reality is currently understood by theoretical physicists, a mental construction that has helped us to make unbelievably precise predictions that have been checked over and over again via countless different experiments. Take a place, a region, anywhere in our universe and get rid of everything it contains. And I mean everything. Strangely, what you are left with is not empty, even though you thoroughly cleared the place of everything it contained. Does that make sense? Hardly. But nature doesn't care what we humans consider sensible. Now, please close your eyes. Why? Because some things around us cannot bear to be watched, and the vacuum you are about to encounter is one such thing. To make sure you are ready, take a minute to relax and think back to the plane ride home from your lovely tropical island. You might remember that you fell asleep not long after takeoff. Indeed, had you asked him, your weird-looking neighbor would probably have told you that for most of the flight you were snoring your head off. So what exactly happened during the flight, while you slept for 8 hours? What time zones did you cross along the way? And indeed, what path does any plane take through the sky when no one is actively looking? All you know about your flight is what you saw before falling asleep and after waking up. You looked out the window and watched as your plane took off from the runway of some faraway island, and you watched it land safely in your home country. In between, no imprint of any flight path was left in your brain whatsoever. You simply don't know what happened. Now, what if someone told you that your plane took a very unexpected route? Via Jupiter, for instance. Or through Earth, like a neutrino, or back and forth in time? I'm guessing you would have a hard time believing it. However, whether dreaming or not, you did experience one such weird trajectory in Part 3, traveling 400 years into Earth's future, in 8 hours of your own time. So we need to look at what happened more closely. You now know that for this to happen for real, your plane would have had to fly extraordinarily fast. Indeed, it would have had to shoot far into outer space, at near light speed, before heading back towards an Earth that had aged fully 400 years. In real life, you may find some compelling arguments against such a trajectory, or against any similarly weird paths your plane might have taken, but still, what if I told you that while you slept, your plane not only did fly out into space and back again, but that it actually simultaneously took all the possible and impossible paths that lead from where and when you fell asleep, to where and when you woke up. Through Earth, and back. Around Jupiter, and back. All of them. You'd probably never take me seriously again, right? Good. That means that you're finally ready to have a look at the vacuum. Your coffee, the vases, your sofa, your home are all gone. You are back in a world that only minds can visit, and you are little more than a shadow, completely transparent and yet delineated. Unaffected by, and not affecting, whatever might surround you. What surrounds you, however, isn't entirely straightforward. As far as you can tell, there is, well, nothing. Only darkness, everywhere, stretching to infinity. By now used to such drastic changes of scenery, you drift gently through what looks very much like a universe emptied of everything it once contained. The view is rather soothing at first. But soon, admit it, you're bored. With nothing better to do, you start reconsidering what I've just told you about falling asleep on a plane. Could a real plane, truly fly in a completely unexpected way? Keeping an open mind about various meandering routes is one thing. but actually flying through the center of Earth? Or back and forth in time? Come on! Well, you're right. Come on is the only natural reaction to such a ridiculous thought. But you should keep an open mind about it all the same, for what may sound crazy for a plane may be very real for a particle. So let us start thinking instead about a particle that no one is watching. You picture it having to travel from one place to another, detected by you only at the points of departure and arrival. Now, the same question again, if you do not look, what path does the particle take to get from one place to the other? Surely it depends. But no, it does not depend. For a plane the idea may seem abstract,